So what's new in logic these days? Logic has been pervasive in almost every device that we've ever seen, but what's changing?
What's changing? A couple of things are changing right now. First of all, the restricted design rules are making difficult to be able to get the densities, power, and performance that we traditionally have gotten, as well as being able to really deal with the power problem at the latest dimensions. Again, that's also exacerbated by the fact that the dimensions are shrinking, and it's all affected by DFM, which means that however we draw the libraries, they don't necessarily appear that way on silicon.
Is that only at the most advanced nodes, or is it happening even at the older nodes?
It's mostly at the advanced nodes where these things become, what used to be secondary effects are now primary effects that affect the ability of the libraries to perform.
So how do you go about solving that? How do you change that? People want the IP, they want to be able to plug it in, but if it doesn't work the way they expected, what happens?
Well, it's a very good question, and doesn't have a straight answer. What we have to do is to work with several areas. Number one, it's a problem that's bigger than just the IP providers. We have to work with the foundries, with getting their design rules correct and how they are extracting their models. We have to work with the EDA vendors, how they take these cells and route them up. For other IP, it's just a rectangular block, typically, that's there. But with logic cells, you give them out there to various SoC designers, and they put them together. And they have to all fit together, work with the multiple EDA flows to achieve the end results of power, performance, and area.
Restrictive design rules typically happen at the forefront of Moore's Law and typically on a process that is just rolling out. As it becomes more mature, does it become easier to deal with some of the issues that you're talking about?
Each different technology has its own story. And again, the fear, uncertainty, and doubt that comes about when a process is new will very often go back and back off on those rules by saying, no, we really want you to do that, but I guess since everybody's screaming about it, we can find a way, and technology can break through to solve some of these issues. Some of them get solved, some of them you got to live with.
Is it pretty much confined to the handheld mobile devices such as smartphones because they have the kind of volume that can justify the cost of developing these new chips, or is it across the board?
We serve all customers. Again, the cell phones, that's a very large part of the LP market. However, we have to be able to develop libraries that work for people from, let's say, the far extreme. They typically use a fast process, developing processors, network processors, graphics cards. They need the standard cell libraries. So do the guys building hearing aids that are trying to make that battery last for 1-2 weeks. And so these different libraries, your same basic gates and flops, have to be able to be designed and characterized and managed so that they work with the low power flows as well. So it's a very, very broad spectrum. So flexibility and having a broad offering to be able to handle all of the extremes is absolutely critical.
How much power out of a typical SoC does Logic use?
Logic will typically use most of it, which means more than half. The memories can be, some chips are, half memory, and a lot of power is used at some of the high-speed IOs, but the dominant area is logic.
So your challenge is to be able to develop, according to all the power-saving techniques, power islands, clock gating, things like that?
We have to have facilities for doing all of that, for retention, multiple power domains, and to be able to manage the level shifters between all of those different domains, and make sure that even things such as isolation cells, if you power down a domain and it has a signal going back to a domain that is powered, you have to be able to handle that with an appropriate isolation cell.
Is there a minimum voltage that you're seeing that nothing is going beyond that? We've been hearing for a while that ultra-low power devices, they just drop the voltage and things will be solved, but there's a problem with retaining charge even within some of the transistors if it goes too low.
Mm-hmm. We run things down to as low as we can. We'll pick something typically 40% off of the nominal VDD as an operating voltage for our logic libraries, and we'll go and once we get silicon back, we run shmoo plots and be able to determine where the actual retention part is that goes beyond what the models will tell us. We have to go back to silicon.
Ken Brock, thank you very much for your time.
You're welcome.